Welcome everyone for today's quantum space-time seminar. Today we are very happy to have Jorrit Kruthoff from IAS, and he's going to tell us about Lorentzian wormholes. Over to you, Jorrit.
Thanks a lot. Thanks a lot for the invitation to speak. So today I would like to discuss some work that I've been doing over the past year or so with Andreas Blommaert and Shunyu Yao. We've been a lot of fun trying to explore sort of particular limits of observables in quantum gravity. And those limits make certain observables very calculable and have nice properties. And I want to start off the talk with discussing a little bit an Euclidean picture. This was some of the work that is done in these papers from last year. There were three groups working on this. There was a group, this is the first reference in Germany, that approached this problem from a more quantum chaos point of view, which is it's a very interesting point of view, using periodic orbits and things like that. And that's also what Douglas Stanford and his group worked on. This is this last reference. And then Andreas, me, and Shunyu, we worked on this using a more intersection theory approach, which is a bit more mathematical, but nevertheless geometrical. And then I'll also discuss a little bit the Lorentzian interpretation of the calculation that we did. I mean, there's of course always different. Like Euclidean is very clear. We know what we do. We know what the definition is. Metric is real. There's no complexification or things going on. In Lorentzian, everything becomes more subtle. Everything depends on certain choices that you make. And we'll see that we made certain choices, and that reflects in the answer and reflects in how we think about things. But we'll see that along the way.
Sorry to interrupt so early, Jorrit, but even the Euclidean is not so clear, because there's the well-known problem with the conformal mode, right, which I'm sure you deal with.
Sure.
There's black magic there too, right? Okay.
Exactly. I think the Euclidean, we can talk about volumes of moduli space, of Riemann surfaces, and they're all sort of well defined and have a good interpretation. But I guess my intuition is mostly from the 2D side, which is of course very biased. But in higher dimensions, things are even more tricky. I definitely agree. Yes, thanks for that.
No.
I mean, it's always good to be grounded back to 4 dimensions. So it's all right. So I mean, the sort of the main theme is that we have observables in quantum gravity, and they can be mostly, I think we're interested in real-time observables, at least in this quantum chaos type of literature that I'll be sort of intersecting with. And those observables you can look at very long times. And gravity is very weak, but still at very long times we can expect certain things to happen. And in particular, in certain controlled settings, what can happen is that at a very long time, things that you thought were suppressed now become very important at long times. And of course, the wormhole and things like the ramp and the spectral form factor, these are very well-known examples of that. And sort of the hallmark of these contributions that become important at late times is that they have different topologies. And what I want to explore is what do these other topologies, what contributions do they give, and can we get a handle on them? Because usually, if once topologies become important, they proliferate, and you have a very hard time summing different topologies. and at least in 2 dimensions you can do it under certain circumstances, but in higher dimensions it's kind of difficult / impossible. All right, so the theory I will be considering is good old 2D dilaton gravity. This will be just JT gravity, and I will focus on boundary conditions where the dilaton and the length of the boundary are fixed. And okay, we have the well-known action with the boundary term, and then there is our topological term. Here we have a parameter S0, which determines the suppression of certain different topological contributions, and they're weighted together with this with the Euler character of the surface in 2 dimensions. That's the theory we want to consider, and of course these the observables that I just talked about that have interesting long time behaviors. The observables that we can consider in our theory are of the form z of beta, which denotes a gravitational path integral with this fixed length boundary condition, and then you can fill it in however way you want, and we can have multiple boundaries, z of beta 1, beta 2, and okay, that's also a well-known contribution to that 2-boundary observable. Well known is that the JT path integral is dual to a matrix model, and that with that correspondence you can leverage a lot of the sort of interesting technology from random matrix theory, which makes this a very almost exactly solvable theory, at least if we don't have any matter. And the correspondence is really that this z of beta and the path integral with boundary condition beta can be computed by this object, this integral over all Hermitian matrices with some probability distribution for those matrices, and then we stick in what we think of as the path integral. So this is like an average over Hamiltonians. And of course here, I mean, this equality should really be in quotation marks, because there is a certain limit that we need to take of this matrix integral in order to arrive at the gravitational. It's a so-called double scaling limit. It's a limit where because usually in matrix models the spectrum is compact, but now in gravity we know that, and the Cardi density at high energies grows exponentially. And to achieve that, you need to zoom into the edge of such a compactly supported distribution, and that reveals the gravitational nature of that matrix integral. And simultaneously, you also scale that the number of states is very large, etc. All right, so that's the correspondence with the matrix integral, and with many more boundaries, you just stick in more of these traces, and you do an average. Now today, the observable that I want to focus on, so let me mention the spectral form factor. The spectral form factor is sort of a very important probe of quantum chaos. It has a very distinctive form. If you look at a quantum chaotic system, in particular, as I've drawn here, so this is the full spectral form factor, sort of the indication of quantum chaos, really this ramp-like region and then a plateau. And this ramp plateau is what shows up in any of these quantum chaotic systems, and it follows really from random matrix theory. And so there's a conjecture that any quantum chaotic system at long enough times can be described by a random matrix theory. And so the spectral form factor is a probe for that, and what will its definition is we take the partition function and we analytically continue in the boundary condition, so beta plus it, and then we take the mod square. And on the side of the matrix integral, that looks like this energy integral or this is more like a spectral representation, and then we have our rho 2-point function. This is the density 2-point function that has interesting features and has a universal form in a certain limit in random matrix theory. And part of the game will be to leverage that universal behavior in a more controlled way.
Right. Sorry, Jorrit, to keep interrupting, but I just
that's fine.
I just wanted to ask you about this statement which many people make, that any chaotic system in terms of the properties, for example, of the ramp, can be modeled by random matrix theory. I'm asking this because some of the systems we have looked at have the same statistics for the nearest neighbor eigenvalues as you get from the Wigner surmise. So on that basis, you might say, oh, they're about as chaotic. But the spectral form factor is different from that in, say, random matrix theory, the Gaussian unitary ensemble or whatever. So I'm just wondering, when people make that kind of statement, are there some ifs and buts, that if these properties are true, then the spectral form factor has to have this universal shape? Just in case you happen to know.
I don't. Well, the short answer is I don't know the specific assumptions. It's also kind of a vague conjecture, of course. I mean, it's hard to make something like this very precise.
Yeah.
The thing I do know is that usually what people, if the rho correlator, right, has this sort of 1 over energy, E minus E prime in this case, square behavior, then I mean you're gonna get this ramp for sure. So that at least does happen.
Okay.
I think it would be interesting, to make that more precise and see, because I think there are indeed I don't remember the specific examples, but I do remember hearing about examples, the ones that you mentioned. Yeah.
Okay. Thank you.
All right. So on the gravitational side, what does this spectral form factor, or the form of the spectral form factor, mean? Well, the leading, so here we have a power law decay. This is just the leading term in the topological expansion. It's just a disconnected part. Then the ramp is the first sort of non-trivial topological contribution that arises. It's perturbative in e to the minus s naught, but okay, from a gravitational point of view, it's non-perturbative. And then once you're on the ramp, there are other contributions that come in with higher genus. And the leading is just a cylinder, but then there can be cylinder with handle, etc. The problem is that when you include all these different topologies, there's certain coefficients that just grow way too fast. And so this is a well-known problem also in string theory, that we get this 2G factorial growth at large genus, and there's no way of summing that. And so, but yet the spectral form factor, I mean, if we really take, if we would really have a quantum mechanical system on the boundary, which would have a discrete spectrum, etc., then this would have to level out and has to have a plateau at sufficiently long times. And the matrix model predicts this, and it's a non-perturbative effect in e to the minus s naught. It's doubly non-perturbative gravitationally, and the gravitational interpretation is unclear. And part of the message today is that you can leverage this genus expansion here. You can take a certain limit of it to make it summable, that also has this plateau-like behavior. It's more like you make an approximation to this curve. All right, so let's get into that. Yeah, you can add matter, that there will be something similar. Right. So the limit that I want to study the spectral form factor in that makes this genus expansion much better behaved is the so-called tau scaling limit. So it's a limit where we take the time to infinity, but we also take this e to the s naught parameter to infinity. So and we keep the ratio fixed. What that means is that sort of you take this plot really, and what we're doing is we're just blowing it up. So we make e to the s naught. I mean, that's sort of the time scale of when this plateau happens. We take that very large, and we take the time to be very large as well, right? So we're scaling it up in vertical and horizontal direction. So it and by doing that, yeah, we'll get a lot of mileage. And so that's the tau scaling limit. That will be the basic limit that we'll consider. Any questions about that limit?
And I guess, sorry, just to make sure, if you had not taken capital T to go to if you had, let's say, I mean, if you had kept both fixed but taken S naught to be large but fixed, then you'd run into this growth of the 2G factorial growth, is it? If you try to include.
Yes, that's right. I mean, you need this T to be very large in order to sort of use some universal properties of this rho correlator, and then that simplifies the genus expansion. Yeah. So why don't we try to do that right now? I have that spelled out here. Right. So and we take t to infinity, but we also take e to the s naught to infinity. So let's look at both of these separately. So when t goes to infinity, right, what happens is that if we look at the spectral decomposition, when t is very large, e and e prime want to be very close to each other. What that means is that this rho correlator, where we can approximate it when the energy levels are very close. And in that limit, the rho correlator takes this particular form. So there is a delta function term, and then there is an oscillatory term. And this whole expression is something that you can derive from random matrix theory. This is just the universal level statistics, but it's non-perturbative. It's a non-perturbative expression. Not only because this one has a funny scaling, so all these rows, they scale with e to the s naught. These are disk densities. So this goes like e to the s naught. And here we see we have a sign of e to the s naught. And so it's e to the I, e to the s naught. And so that's doubly non-perturbative, yet it's order 1. And so this contribution is oscillatory and very, very important. Now, the funny thing is that when we take this t to be very large and we use the random matrix theory, we stick that in this expression for the spectral form factor, then we can just do the integral over the energy differences. And the only thing we're left with is an integral over the overall energy, right? And that's somehow a little bit peculiar from random matrix theory, because usually what you do is you pick some energy in the middle of the spectrum, and not close to the edge, and then you just look at the nearest neighbor distribution of the energy levels. You don't integrate over the energy over the full spectrum. That's not something that you usually do. But here, this full expression of the spectral form factor, we want to integrate over all energies, and we're not looking at some fixed energy observable. And so that's sort of a different thing. And well, the expression that you end up with is this expression, and yeah, the fact that it has this funny behavior is really because this sine square has a very simple little Fourier transform, right? It's just a ramp and a plateau. That's what this cinch does. Okay, so this E of x here is the inverse of the disk density of states. And okay, there's some funny. So here I've written everything.
Sorry,
in terms
Jorrit, just so to make sure that I understand this.
Yeah,
now that in this tau scaling limit, the plateau happens at an order 1 time, and there is
yes.
no decay basically, right? It's just
Yeah.
ramp, and it hits a plateau at order 1 tau.
Yeah, that's right.
Okay, great, thank you.
That's right. That's right. So yeah, I mean, to answer Onkar's question even further, you can see from this expression that it's a finite integral, right? So this integral there's a finite number, we can calculate it. So there's no asymptoticness anymore. There's nothing funny to do with that. And in particular, because this tau. So here I've written everything is still in t and e to the s naught. But if you write everything in terms of tau, as I've done here below, you see that everything is just a power series in tau, right? That follows very simply from this formula. And what you see here, right, is that these contributions are all sort of associated with certain topologies in the gravitational path integral. And so this first one is really the usual wormhole. And the second term here, the tau cube, is a wormhole with a handle, etc. And so there's certain coefficients here that in the usual case, if you want to calculate this, not in the tau scaling limit, but just calculate it, these will be the ones that grow factorially, and so these will be the bad actors, so to say.
So, sorry, Jorrit, just to make sure, rho d is going like e to the s naught, right? Is that right?
Yeah.
Okay, good. I'm with you.
Yeah.
Thank you.
Sorry, and in the usual case that you were talking about, you would have, let's say the tau to the 5 would have an e to the power minus 5 s naught, I suppose, and then many powers of t. And the simplification is to keep the largest power of t, the t to the 5. Is this right?
Yeah.
Okay. So this largest power is much simpler than keeping the whole series.
Exactly.
Okay.
It's actually just on that point, it's the constant term at each genus that gives you a problem. That has the largest growth in genus. But yeah. So yeah, just to elaborate on the point that Shiraz is making. I mean, the geometries with long boundaries, if we would calculate this in Euclidean sense, are the geometries that contribute here. Right. So in more generality, when we do the Euclidean calculation, we would expect an expression like this, right? We have some coefficients, VAB, we have beta 1, beta 2, and they're raised to some power. And that power is bounded by the genus. And when we want to do an analytic continuation, what we would expect to the largest power to be is t to the 3g minus 1, and which is not the same as what we would have here. This is more like t to the 2g plus 1. And so that's sort of a puzzle. And why does that, after we do the analytic continuation to Euclidean, to Lorentzian signature, why does that happen? And it turns out that there are sort of very intricate constraints between this coefficients VAB that actually people back in the 90s, in terms of this intersection theory, have already found certain relations between certain topological observables, and they turn out to constrain this expression in such a way that the maximum power is t to the 2g plus 1 instead of this 3g minus 1. So that's a sort of a funny math. Yeah. Right, and a few other comments are that this small tau expansion, if we look at the expression that we have here, the variable x here is really sort of an energy variable. And so when we do a small tau expansion, we're really doing a low energy expansion. And that low energy expansion is also leveraged in Douglas Stanford's work to argue that at small energies, there's actually large quantum corrections that need to be taken into account to arrive at the correct answer. Sort of large energy or large quantum corrections that people previously in the quantum chaos literature didn't take into account, and they give rise to some interesting structure. And because usually you would expect if you fix the energy, you would just get a ramp and a plateau, and that's it. But that's sort of at some reasonably large energy, like somewhere in the middle of the spectrum. But when you lower the energy, and especially when you integrate overall energies, there's going to be corrections at small energies that are very important, and that give rise to these other powers in time. And so that's also something that we see here, right? The small tau expansion and the other non-trivial powers that you're getting really come from some low energy regime. All right. Yeah, and the other one it only works for monotonic rho. Any more questions about this? Right. So then let's try to think about these geometries or this calculation in Lorentzian signature. So I want to argue that we can obtain this result also directly from a Lorentzian signature. And it will be more like treating the geometries as geometries in light cone gauge, as we would usually do in the light cone string. And as a byproduct, I think what is very nice is that the parameter counting becomes much easier. And by parameter counting, I mean that the powers of t, you don't need to go through this whole song and dance of trying to see that there's cancellations, etc. You can just look at the geometry and simply count how many moduli there are, and that gives you already the power of t that you want, or that you expect from the Euclidean calculation. And sort of what I started the talk off with is that there's going to be different choices on how to think about the Lorentzian geometry. What I want to do here, the sort of the point of view, is that the Lorentzian geometries are everywhere Lorentzian, except at some isolated points. And of course, we know that geometries cannot really be, if we want to allow for different topologies in Lorentzian signature, they can't be Lorentzian everywhere. I mean, there's going to be the point where the topology changes, even if we shrink it to a point, that point is going to be a point where the metric degenerates. And sort of an example of that, an easy fix to that degeneration point is the double cone, which is responsible for the linear in time behavior of the spectral form factor. So that will be the first leading term. And that's the well-known geometry that we take the black hole geometry and we compactify it using a boost. And so here I've written the zero temperature version of that. And it has at its apex, there's a cone-like singularity, but we can avoid this by slightly going to Euclidean signature here. So there's an I epsilon here that lets you avoid that point. Okay, this is what I said about the geometries more generally. If you want to have other Euler characters, it's going to be impossible to write something that is purely Lorentzian, and yeah, there's going to be issues with that. So if we want to keep all these topologies floating around, even in Lorentzian signature, we need to make some choices. And the choice that we're going to make is we're going to look at solutions. And so these are, I'm going to sort of, I mean, there's not really solutions to the path integral, but more configurations of this form. And so the instead of this curvature to be -2 everywhere, I want to have some locations where there's a delta function source. If I have this sort of delta function source, I can engineer the, with the specific coefficient, I can engineer the geometries to have a particular Euler character. And the way, I'm not sure I'll get to that point entirely, but the you can, even though these are not sort of saddles of the path integral, you can make them saddles by introducing a new parameter, and we call these constrained instantons. We introduce a new parameter, and we just think about doing a saddle point in that parameter as well, and then you can think about these geometries as on-shell solutions, and they have some nice geometric interpretation. So I think they're worth investigating.
But Jorrit, is there some motivation from maybe the Euclidean path integral or something like that, which you could highlight? Okay, this is why you might want to consider geometries or configurations like this. Or I mean,
yeah. So
okay, go on.
I'll take a little bit of a different from Euclidean, but the reason, well, one of the reasons is that for instance, in light cone string, we would also consider these type of geometries. They will also, I mean, they're all everywhere well defined, except on some what they called interaction points. Right. That's where there's some delta function. They're slightly different than those, but that might be one reason that this is not crazy. The other one is that there's an example in flat space which and how to think about the pair of pants, for instance. Like if we have a pair of pants geometry, how can we, if we think about some transition amplitude between one universe and two universes, like is there a geometry, like what would that mean? And sort of there's a very easy way of thinking about it is just a diffeomorphism that's everywhere well defined, except at one point. So, for instance, you could look at a double cover diffeomorphism, as I've sketched out here, and we can look at this coordinate transformation, which is a double cover with the branch point at the origin in the xy plane, and okay, that has this type of curvature, and geometrically, we can think about that as in this way. We have two. I hope this picture is a little bit clear. There's a lot going on, but we have two planes, two xy planes, and there's a cut running along the y direction, positive y direction. We can choose that to lie along there, and then the pair of pants geometry is obtained by gluing along the similar colors, right? So here we glue along yellow and green and the other ones, and then you arrive at a geometry that looks like this. And so these are just pieces of the Minkowski plane that you patch together, and so these are topology changing solutions or topology changing geometries. And they will have this degeneration point yeah. So that's one of the motivations of why we would like to consider these geometries.
Right, but the thing that was worrying me is that, I mean, if you're out to do the JT gravity path integral, then how do I think of the fact that these configurations? I mean, I guess you're just saying these are some configurations you have to integrate over, right? Is this the thing?
Yeah. So what I'm doing is that so I have these geometries. I think they're very mild modifications to the usual saddles, and you can introduce like some parameters in the path integral. You can just manipulate the path integral so that you'll end up with these solutions being saddles. And sort of one of the parameters that you introduce will turn out to be this sort of energy integral that we saw in the beginning. This integral over x in the spectral form factor expression. So yeah, it might be a bit sort of controversial to introduce these solutions, but I think they're very interesting solutions that have that do give you sort of the answer that you want, and they have geometrically interesting properties.
Thank you.
Somehow they remind me, just I don't know if there's anything to this comment, but in the Euclidean, in the ADS context, of course, as you know, various people, Witten, Turiachi, etc., I don't remember all of them, introduce these exponential potentials. And if you then do the integral, then you in effect are introducing these conical deficit angles proportional to the value of the exponent, e to the alpha phi. But you can relate the curvature deficit in that case by analytic continuation to the moduli you would associate with extra handles, and so somehow that problem where they were introducing these delta functions in the curvature gets related to more complicated topologies, through analytic continuation, of course. And it somehow seems something similar. I don't know.
Yeah, I mean, it might be. Yeah, I have not made that connection precise. My collaborators also didn't, I think. But yeah, that's perhaps another good intuition, that taking the Euclidean geometries and continuing them in a suitable way would arrive you at these type of geometries. Yeah. Thanks for that comment. But yeah, I mean, Onkar, I do agree that to some extent I'm pulling these solutions out of my head, and I'm going to work with them and then see what they give.
Okay, sure. Thank you.
What I do like about them is that, I mean, that you can think about them as diffeomorphisms that are sort of not well defined at one point, and that there's sort of not I think, for instance, way back, Gary Horowitz also was looking at topology change, but from a more gauge theory point of view. And there you have the Einbein or whatever, the Vielbein needs to be invertible, etc. Right, and that says that the gauge group is a certain group, and you have your gauge theory to describe it with. But he was making the point that, perhaps if we want to have a sort of topology change, we need to enlarge this gauge group to allow for singular diffeomorphisms. So that's another comment. Yeah. All right. And sort of this sort of, as I was explaining, the pair of pans that you get in this way, really the geometries that we have are locally, there's like some pair of pans splitting going on, and this cutting and pasting construction that follows from these singular diffeomorphisms is something that you can also carry out on, say, the double cone to create an extra handle, right? So For instance, what you can do on the double cone is, you have to, the extrinsic curvature is changing, so you have to be a bit more careful. But you can define these slits, and you have an diffeomorphism that's not well defined in some interval, and you do exactly the same on the other side of the double cone, and then you glue them together, and that creates a handle. And so that will be our proposal for a genus 1 surface in Lorentzian signature.
Sorry, just so I make sure, in this picture, the dots are where the curvature delta functions are, or I didn't understand the diagrams.
Yeah. Sorry, let me maybe explain. So here we have these slits, and these slits are really sort of the same as the branch cuts here. Okay. And the singularity is at the dots. Okay. But of course, we identify, so there's only two singularities, two delta functions in this case, and those two delta functions they give you the Euler character that you want.
Thank you.
Yeah. So that's the proposal, that even in Lorentzian signature you can also have this type of geometries. And yeah, that this is a point that this point below here is a point that was raised already. So let's discuss that a little bit more.
Sorry, your boundary is close. Circles in Lorentzian time.
Yeah. We want to keep the boundary Lorentzian. Yeah.
I see.
Yeah, so it's a circle in Lorentzian time, just as with the double cone. Yeah.
Okay. Yeah. Is that not an unusual thing to do, to have Lorentzian time a circle?
Yeah, I mean, of course, I mean that's a bit of a funny construction, but I think it is the right one for calculating something like the spectral form factor. It's really an analytic continuation of the Euclidean calculation.
Okay, so you're just continuing the boundary Euclidean circle to a Lorentzian
Yeah.
circle.
Or complex in general. Yeah, okay. That's right. Yeah.
Thank you.
Yeah, I mean, it's true. This double cone and all these type of geometries, they're kind of weird. But it turns out that like even if you consider like matter on these type of geometries, things are okay. This sort of apex thing is also okay. Like you can regularize it. It also, these singularities that I introduced, you can also regulate those. There's a nice paper by Louko and Sorkin where they do this in flat space, but these things can be regularized. So the double cone is kind of a magical geometry, and I don't understand it 100% like what the precise meaning is, but it seems to work, and it seems to behave nicely. But yeah, it's the Euclidean continuation, the Lorentzian continuation. All right, so let's try to see how we can bring these geometries back to life semiclassically. So,
sorry, one more question, if you don't mind. If I cut this picture on a slice, this would, and let's say I'm looking at the left circle, the left boundary. My slice, I would imagine, would cut this left boundary in two places. So this looks like I've got two copies of the boundary Hilbert space, if I'm allowed to think that way. And then I go up in time, and then at some point it becomes one copy. Is this? I mean, I don't really know what my question is, but it's sounding interesting. I was wondering whether you had any.
Let's see. Yeah, if you cut it, well, but I mean, if you cut it and then continue, like the boundaries, they won't come together again, right? I mean, I think when you evolve with the global Hamiltonian with just time evolution upwards. I mean, this geometry, you obtain it by taking the black hole and so you have the boost generator, and you compactify the geometry with that boost generator. So and that's the geometry. Now you can cut it, yes, but question is, okay, how are you going to evolve? If you're going to evolve with the global Hamiltonian, you're just going to go upwards. These things do not come back together. I mean, you'll have some entangled state on this side, right? But yeah, they will just evolve.
Yeah, but sort of if I just chose to my own evolution operator, not necessarily some killing vector, I just chose to move up, I would have these two Hilbert spaces, which would then come and sort of merge. Oh, maybe it's very stupid.
Why are you saying that they merge? Like from the boundary point of view, you have two circles, right? And they're just like going on their own journey.
Let's forget the right circle. Okay. Let's keep the left circle. Now, okay. I was thinking of cutting the bulk across a spatial slice.
Ah, I see. Okay.
Now, that cuts the left boundary at 2 points.
Right? Yes.
Now, I'm taking the spatial slice and moving it further up so that the thing I'm trying to make, I was trying to make, precise the fact that I found having time being a circle weird somehow. Yeah.
Right.
Yeah, I mean, I wouldn't know what type of evolution operator, because I mean the time translation operator in this geometry just moves you around in this circle.
Yeah, so, it's fine. It's fine. So probably a stupid question. Yeah, please go
on. No, but yeah, I don't know. Okay, let's look at these constrained instantons. We can look at it in a simple geometry with just one boundary. I mean, it's a little bit like what Shiraz was asking. In Lorentzian, we'll have a purely Lorentzian boundary, and we obtain that from this path integral. We compute in Euclidean signature. We set beta to be IT, and that will be the definition of our Lorentzian. But what will be the path? I mean, if we want to do the path integral, what is the geometry that we care about? Yeah. And one thing that you can do is insert this one, and so I want to look at what the Lorentzian geometry is, and that has these boundary conditions, and because I mean we cannot, since this has non-zero Euler character, right? It's going to be hard to find a geometry in Lorentzian signature that satisfies the equation of motion everywhere. So what we're going to do is in the Lorentzian path integral, we're going to insert this factor, right? This one. So it's an integral over A, 1 over the volume, and then we integrate this delta function over all space-time.
Sorry, and is X here defined in some diffeomorphism invariant way, or I mean, how do you choose X, phi of X?
And this is just the I guess the volume element.
No. You're integrating over it. Sorry. Thank you. Sorry, that was stupid. Yeah, sorry, I got it.
Yeah, we're just integrating. That's right. Right. So then this delta function we write as a Fourier decomposition and with alpha. So here I wrote it in a bit of a funny way, but you'll see in a little bit why. And now you can see already that we have this phi here that is going to change our equation of motion, right? And precisely with the delta function. And so this is the piece that this is sort of the reason why we're going to do this in this way. These geometries, the saddle points will now be slightly changed. We'll have another weighting factor that depends on A, depends on alpha. And so alpha is sort of a parameter of the geometry that you need to integrate over, but we will take a saddle point approximation and compute the contribution in that way. And then this integral A that integral is really sort of the energy integral. That it's like the integral over the area, you know, and as you can see here, the A is, I mean, the value of the dilaton is sort of a proxy for the area. But yeah, we're integrating that over the full real line, and so that's maybe slightly weird. Then if we manipulate so that the volume and etc., that they can be computed, this insertion of this e to the phi is really akin to what Sandeep was also asking about, defects. And so if we do the full path integral, and we do path integral phi and over the metric, we get this factor here. This is the contribution for the path integral. And then we have an integral over alpha left, and we have an integral over A left. Now, what is interesting is that there's a saddle point for alpha, which is at this particular value. And so the equation of motion really that this geometry satisfies is this equation, and where this term comes from this extra e to the phi expression. Is that clear? Okay, perfect. And so with these, and okay, then you can do the A integral. Okay, there's some subtleties with convergence, etc. But you can regulate that and make it converge, and show that this Lorentzian path integral at IT is really equal to the Euclidean calculation where you've analytically continued. And so the proposal is that this geometry that satisfies this equation is the Lorentzian geometry that you care about in the Lorentzian path integral. And what this geometry really looks like is really just half of the double cone. It's this cone-like geometry. There's a boundary that has length t, and it has a parameter in here which is related to sort of the angle, deficit angle. That's A, and it's everywhere satisfies the equation of the usual JT equation of motion, except at this tip. At the tip, it doesn't satisfy it, and it has this sort of delta function, but with a complex coefficient. And this is precisely, if you now calculate the Euler character, I mean, with this equation, you can calculate the Euler character. You get precisely the Euler character for the disk that you expect. And this sort of additional term here, this 2i at is really canceling the contribution from the Lorentzian boundary. And so what you're left with is really only the Euler character, the bulk Euler character piece that you want. And so just maybe this is another answer to Omkar's question, is that these geometries do make their appearance also in more mundane, like we don't care really about topological expansion here, but they do appear. I think this construction was put forth by Don Marolf in a paper from some time back, but where he also argued that these type of geometries are necessary.
And then I guess you have to integrate over A, as you were saying, huh?
Yeah, that integral, of course, because of this funny factor here, is going to be a little bit problematic, but you can regulate this, and we stipulate that in the paper. All right. Now for the double cone, you can do exactly the same. Okay, there's some minor changes. And you can again have these delta function type contributions. here, of course, we make an assumption that the alpha integral. So here the alpha saddle point evaluation of alpha. I mean, this is a Gaussian integral, so it's going to be exact, and there's no doubt about this validity. But in the more general setting, where we have say the double cone and different genera, we don't have a clear answer of and what we would want is to set alpha to 0, and that those are the geometries, and the minus 4 pi times the delta function are the geometries that I displayed before that I would like to have, but that would require this setting this alpha to 0. And so there's an assumption in our construction that which I think is an assumption that okay, our results are consistent with Euclidean calculation, so there's at least some meat to that assumption, but it is an assumption, and yeah, right. I think these yeah, again, metric is degenerate at x naught, where the topology change happens, but we can deal with that, and it's all fine. All right. Now another.
Sorry, Jorrit, I didn't fully. Okay, could you just say once more what the assumption you made was?
Oh yeah. Sorry, maybe I brushed over that. The assumption is that look, so we have these are the equations of motion after we introduce the constrained instanton. The solutions that I want have alpha is 0. So on the double cone, I want alpha is 0, because then I have this minus 4 pi times the delta function. And when I calculate the Euler character, then I have the required Euler character.
Isn't there like a specific action for alpha which controls the saddle point, or not?
Yeah, I mean, but it's very hard to calculate alpha.
Okay.
Yeah,
I see. So the assumption is that whatever saddle point you get by doing the alpha integral will be at alpha equal.
Yeah, that's our assumption.
Got it. Perfect. Thank you.
Exactly. Yeah. Yes. All right. So no further. I mean, I think I mentioned these things already. The double cone is compact, so we need these finite sized slits, and we need to glue in a particular way. But I mean, this can all be done, and you can get a smooth gluing, and you arrive at the geometries that I mentioned before. Now, if
one more question. What determines how many of these insertions you have? Like one defect, 2 defects.
Yeah, so I mean that's I mean, if you want to look at a particular genus, then there's a certain number of slits. Like for every genus, you need 2 slits that go together.
Oh, okay.
Yeah.
Thank you.
Now, if we look at the path integral contribution of these geometries, then we get an expression something like this. So each we have an integral over the double cone, and so we integrate over all the positions of our defects, of our slits, and they're weighted by this factor, the value of the dilaton at the singularity, and then we have the usual topological suppression. So for each branch point that we introduce, you get this type of factor, and then there is this factor just comes from the rest of the on-shell double cone solution, right? This is just the e to the minus 2 beta energy. And what is nice is that, okay, we have this integral over the position of these branch points, and really what we can combine these two guys together, this really becomes the area, at x naught. I mean, here the phi of x naught is really the area, right? And okay, we incorporated as naught as well, because that's also sort of an area. And so what you see here is an expression that we need to integrate over the position of the defects, weighted by this area term. Now, so what does that mean? And this has some interesting implications. One of them is that that when we look at the double cone, the area only depends on sort of the radial direction, and there's a time symmetry, so that nothing will depend on the temporal coordinate. And you'll immediately get that each crotch contributes a factor t. Sorry, I say crotch. It's a bit of a weird word, but yeah, it's fine. So that's how you very easily with these. So for each slit that you've glued, you get 2 factors of t. And so I remember that in the Euclidean calculation, that was precisely the t to the 2g was precisely the t to the 2g plus 1 was the power of time that we wanted for each. That followed from the Euclidean calculation. So that's precisely the power that we want. And here we see that and the double cone itself has a rotational symmetry, which gives you 1 factor of t. But then each sort of handle in the Lorentzian sense gives you 2 powers of t because of these spatial because of these integrals that you need to do over to the position of these branch points. So that precisely gives you already the t to the 2g. And now another interesting point, I think, is that there's still, after you've done the temporal integral, there's still the radial integral to do. But then you get something funny, right? That the radial integral can be done now with saddle point, and all the branch points want to be very close to the bifurcation surface, and they want to be close to the extremal surface. So that's a sort of a funny feature of our construction. But all the topology change wants to accumulate close to the bifurcation surface. It's not at the bifurcation surface, but slightly away from it because of this square root g factor. But yeah.
Is that simply because square root of g becomes smaller as you go radially inward, so to say?
Yeah. That's right. That's right. Yeah. So that square root g, I mean, that provides a little bit of pressure that these crotches are not exactly at the and because this guy will just push you back to the origin. Right, I think I mentioned this. Yeah, and then there is a final energy integral that you need to do, and it's sort of the A integral, which is since we're all working here in semiclassically, right? We cannot compute this coefficient for the t to the 2g plus 1 exactly, because as I mentioned, I think the calculation of that coefficient is very complicated. You need to be able to have full control over the path integral. In Euclidean signature, you do. So I mean, there's a bit of a trade-off here. Like, you can either make the power of t like manifest and very intuitive, and you have a geometric understanding of where it comes from, or you have difficulty calculating the coefficient, and which would require having full control over the Lorentzian path integral in this part with this constrained instantons, and with the gauge that and you need to gauge fix, and etc. It becomes kind of complicated. Or in Euclidean signature, and the calculation of those coefficients is sort of relatively simple. but the power of t sort of comes out in a sort of magical way, and it's not really clear what it means. But so I think they're sort of complementary approaches. And another thing is that in the semiclassical approximation, random matrix theory would actually say that this whole coefficient is 0, and because it's just a ramp and a plateau, and because the energy is large, in the semiclassically, you're just not getting the small energy contributions that give you all the fun. And so, yeah, semiclassically, I think we have an argument that indeed this coefficient is 0, and that there's certain contributions at low energies that need to kick in, but yet again, we cannot calculate them using our approach.
I mean, by semi-classically, you just mean they're suppressed in the genus expansion? No, you meant something else, I think. I didn't quite.
Yeah, I mean large energy. Yeah, the energy is large. Yeah.
I see. So at large energies, they are suppressed. I see. So it's not the e to the s naught effects. That's not what you're talking about. It's the energy effect, is it? Some dependence on.
Yeah, I mean, well, in this, maybe I can go back to this this expression here. You see that the tau scaling limit, so the expression that we arrive at here. This expression really, you see all these different powers in a low energy expansion, and meaning that if t is if you do a perturbative expansion in t, this integral, you can approximate it, and the x variable is really an energy variable, and so you're integrating the energy over a tiny window, very close to 0. And so that is what I meant with when you're doing this perturbative expansion in t, you're really integrating this x over like a tiny region in energy, and that gives you all these non-trivial powers. But if the energy is very large, then yeah, you're just getting a ramp and plateau, and there's no other powers.
Okay.
Yeah, so it's a bit of yeah, so I think that's what I wanted to tell you guys about. Thank you.
Thank you so much, Jorrit, for the wonderful talk. I know it's getting late here in India, but any further questions for Jorrit? Okay, let me just ask one question. Sorry to delay you guys further, but so I didn't fully understand from the Lorentzian point, from the Euclidean point of view, I guess I understand that these higher genus contributions are sort of, we thought of as like you're in the prescription there is that you sum over these higher genus contributions to the Euclidean path integral from the gravity point of view. Now here is the prescription that in the Lorentzian path integral you have to sum over these insertions?
Yeah.
Or but I mean I got a bit confused because it seemed to me that you were saying that these insertions just come from inserting 1 in the path integral. So that confused me because I could have inserted 1 in any number of ways I wanted, but why should I sum over that, right? I mean, it seemed to me, I think I'm just misunderstanding this, but it seemed to me that you were saying that I can just insert 1 n number of times and just sum over n. But is this not right? This is not right, right?
Well, I think if you would take the path integral,
okay,
and you say, I mean, I think it's a little bit of a choice of what you mean with the geometries that you integrate over.
Okay.
And I think what like for instance, I think you could rephrase this this path integral as well as a path integral where you because if you just take the path integral at face value and you just start integrating, you're not going to get any topology change, right? I mean, you need to make you need to change something to get topology change, right? Because I think any geometry that in Lorentzian signature has topology change will have somewhere where the metric degenerates.
I see. Okay.
Okay. And you can also say, okay, I'm gonna integrate over complex geometries, and okay, maybe that works as well. Okay. I think the point of view that we wanted to take is that, okay, more of an extreme point where you push the all the non-Lorentzianness to isolated points. And like one way that might be equivalent is that you integrate over the dilaton, but you integrate at certain, you leave certain points of the dilaton, certain values of the dilaton fixed, and then you later integrate over those. I think that will also introduce these delta functions, and then you can construct different genera. But I agree that sort of the next step, that summing over those different insertions, I think it has to do with sort of how you're defining the measure and the path integral.
But maybe it's just a way to do the constrained instanton calculation in a way so you pull out the relevant genus contribution. I mean, maybe, you know.
I agree with that. I mean, that's definitely true. I guess I thought maybe Onkar was asking about more sort of how you would see that from the usual path integral, like not doing any constrained instantons, like why. But I agree that we can make all these geometries alive by doing the constrained instanton, doing the sum, and just demanding that you want to sum over genus, and then you're obliged to put in different insertions. Yeah.
I see. Okay, yeah, thank you. And thank you, Sandeep, also for that clarifying comment. Are there any further questions? Okay, if not, let's thank Jorrit again for his very nice talk.
Thanks a lot. Thank you.
Yeah, thanks a lot for the questions. That's great.
No, thanks so much for taking the time. That was very nice.
No, of course. Anytime.
Okay, sure. Okay.